Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. In the last few classes, we have basically studied various numerical schemes, and we also discussed about the modified PDE, basically modified partial differential equation, which says that when you apply a numerical discretization to a equation, any differential equation, you are actually not solving that particular equation, but it has got certain extra terms. Okay. So, and we through the modified PDE we learned something about the stability and for example, why the central differentiating is in a convection problem is not stable, and so on and so forth. In today's class, we will look at the numerical stability in a more formal way. Okay. So, we know from the Lax equivalence theorem. So, as if you recall, we have discussed about the Lax equivalence theorem, and what it says is that convergence is equal to consistency and plus stability. So, you know that for convergence stability is very important. In a if you define this Lax equivalence theorem, so this is the Lax equivalence theorem. Okay. So, for a consistent scheme and for a well defined problem, the stability is the sufficient and the necessary condition for convergence. So, it is a necessary condition. So, we need to basically find out whether the scheme that we are going to use for solving a particular problem is stable or not. Okay, so we will discuss, there are several approaches to analyze the equations, analyze the schemes for the stability. We will discuss something called von Neumann stability analysis. This is one of the earliest and most common stability analysis that is used, and it is proposed by von Neumann, who is also father of computing. Okay. So, all the stability analysis that you have in the literature, not only von Neumann, but you have matrix analysis, and there are some other approaches. They are all based on basically representing your variable in a Fourier and such. Okay. That means we will represent in a basically frequency wave number mode. So, you may have u of t and x, and that will be written as u tilde of maybe omega and k, right. And why do we do that? Is because it is easy to analyze any wave than any arbitrary signal. Okay. So, for example, you might have solved the wave equation in your school or in your college. So, if you have like del to u by del t square equal to c square del to u by del x square, right, u to t equal to c square u x x, right. So, if you assume u equal to e to the power I k x minus omega t, right. So, then it you can basically separate the t and x and you can solve it exactly, right. So, the wave basically gives you a handle to analyze the any particular problem in a very convenient way, right. But then you might ask question that your signal can be of any type, right. So, when you solve a flow problem, okay, so let us say if you want to solve this linear convection plus c del u by del x equal to 0, once again this both are same, okay. if you take a double derivative and try solving it, it will give you the same equation, right. So, you can say that u can be a square wave function, uh, it can be sine, cosine, or it can be an exponential, whatever function you want, right. So, why you are considering that u as a sine wave. So, what I am saying that when I am performing a stability analysis, if we consider u as a harmonic mode or a summation of harmonic modes, right. That means it is represented in terms of Fourier series, right. I am sure you must have read about the Fourier series, right. So, why we are considering the Fourier series if our signal is not necessarily sinusoidal is because I mean by definition if you consider the infinite modes. So, all of these modes can come together and give you the whatever signal that you want, any arbitrary signal, okay, can be represented in terms of basically superposition of different sine and cosine waves. Okay. So, that is by definition. In fact, we have been analyzing these square waves, okay, or the step functions. Okay. In fact, if you want to represent this in terms of sine wave, so you can see there is a discontinuity here, okay, and the sine wave goes like this, right. So, you might wonder that how you can use the sine wave to represent a square wave, right. But you can do that. So, one way I want you to go back and try it, that plot a signal, let us say x t equal to sine omega t, okay, and so you can, if you make it x t, so this will go like this, right. Now, what I want to do, I want you to do is basically let us say x 1 t is basically sine 1 by 3 sine 3 omega t, okay. So, you decrease the amplitude by 3 and multiply the frequency by 3, increase the frequency by 3 third factor, okay, by a factor of 3. So, this if you plot this and then you keep on adding, okay, do x 2 t, okay, that will be sine omega t plus 1 by 3 sine omega 3 t 3 omega t plus take all the odd functions, okay, odd multiples 1 by 5 sine 5 omega t and plus 1 by 7 sine 7 omega t. And if you do that, you will see that quickly you will start basically seeing the sine wave is coming very close to your square wave. And if you can consider that you are taking to the infinite number of such waves and keep on adding like that, okay, so that will become like a square wave, right. So, even the square waves can be represented in terms of sine wave if you consider the infinite number of sine waves, right. Of course, wave limit we cannot go to infinity, but you can get a good representation even for the functions which are not completely continuous, okay. So, so that is why we will stick to the representation of u into the harmonic modes and we will represent it on a grid. So, how do you represent it on a grid? Okay, let us make a grid, okay. So, you have a grid and we will consider uniform grid. So, before I go there, I want to tell you some limitations of this von Neumann stability analysis, okay. One is that it is only basically applicable to basically linear equations with constant coefficients, okay. However, you might say that most of the equations that we solve in the fluid dynamics are non-linear. So, how this stability analysis will help, right. So, despite of the fact that there are some limitation or some restrictions about this analysis, you can use this analysis to get very useful information even if you are solving the non-linear problem. Your problem, the equation may be non-linear, but it may be locally linear, okay, and there also whatever outcomes that we get from the stability analysis will be applicable. And on the other hand, and also like if your equation is non-linear also, there also it does not give you the sufficient condition, but it gives you the necessary condition. So, from the stability analysis you will get the necessary condition, but you might have to consider some more factors if your problem is non-linear, okay. The second is it assumes the domain is periodic, okay. or basically it is only applicable to interior domain, let us say if you do not have the periodic boundary condition. Okay. Again you might ask question that most of the practical problems are not periodic, right. So, we cannot basically use the periodic domain or periodic boundary conditions, but even in those cases these stability analysis can give you very useful information for you to consider. Okay. So, there are some more limitations of this analysis. For example, the time update that you have should not have more than 2 steps. Okay. Updates should not have more than 2 steps. Okay. So, there are these are some of the limitations that you have in the one Neumann stability analysis, but despite all these limitations, this is a very useful analysis, and that is why we will continue with this. The other thing that we have is that let us say that you are not very happy with this approach and you want to go to full fledged about learning about the scheme that you want to solve for a nonlinear problem, that is used for a nonlinear problem. Unfortunately, you have no means to basically do the nonlinear stability analysis. Okay. So, this is not only kind of requirement, but it is the only approach that we have in our hand to study the behavior of the numerical scheme, right. Even the similar approaches also consider, or they also have similar limitations, right. So, now let us make our grid. Okay. So, let us consider, okay, let me just erase this. Okay. So, you can have all in the uniform grid. Okay. So, this let us say this is the size that we have delta x, right. So, now let us say that we want to represent any signal or any input function that we have in terms of sine wave, and we are representing that on this grid. So, what is the minimum wavelength that you can basically resolve with this? So, minimum resolvable wavelength. Okay. So, that is lambda minimum. What is the minimum wavelength that you can resolve? So, if you look at the size is delta x. Okay. So, if you want to resolve let us say sine wave here. Okay. So, what you require is basically 2 delta x, right. So, that will become minimum that can resolve it 2 delta x, right. This is also called the Nyquist criterion, okay, or Nyquist frequency. I mean you can basically interchange the frequency and wavelength. Okay. Okay, so you can read more about it. So, then the maximum wave number that you can resolve is will be basically max will be 2 pi by lambda minimum, that will be 2 pi by 2 delta x will be pi by delta x, right. Similarly, what is the maximum resolvable wavelength? Maximum wavelength that you can resolve, okay, that will be lambda max, and if the domain size let us say is L, okay, and because we are considering it to be a periodic domain, so you can extend it by minus L on this side. Okay, this is basically L, and then you can put the maximum the wave of the biggest wavelength, right. So, your lambda max becomes your is equal to 2L. Okay. So, your minimum wave number k minimum will become 2 pi by lambda max is equal to 2 pi by 2L, that is nothing but pi by L, right. So, why did you find the maximum wave number and minimum wave number? Okay. Because whenever you put a grid, okay, basically you limit what is the maximum number wave number that you can resolve and what is the minimum wave number that you can resolve, right. So, what is the kind of harmonics that you can represent using this grid? Okay, you can represent. So, this is not only delta x, you can have basically 2 delta x, 3 delta x. So, this is the minimum wave number. You can have 2 into pi by L, 3 into pi by L and so on and so forth, right. So, you can basically write it like that, right. So, all harmonics that you can represent here. So, all the waves are representable on this particular grid. What is the grid? So, grid goes basically 0 to all the way to n delta x, right, where n delta x is equal to L. So, L is equal to n delta x, right, delta x into n. Okay. So, then you can write, so what, how they will be represented, kj. So, this you have k mean and k max, but we want to find out all the wave numbers they are representable. So, then you can write j into pi by L and that will become j into pi by n delta x, right. So, these are basically you can take j equal to, so j will be basically 0, 1, 2, 3 and all the so on and so forth, right. And you can compare with the Fourier series definition you have, where you write basically a0 plus a1 and then you have basically sigma, you can write ai and cos pi n and so on and so forth, right. So, similarly with the cos sign term also. So, this is a0 is nothing but j equal to 0, right, which is where it is a constant, right. So, you can represent all the waves, that is represent using all the waves with the wave numbers kj, right. So, then you can basically define your phase angle, okay, which is phi j, and phi what is phase angle? Phase angle is basically is nothing but kj into delta x, that will become j into pi by n, right. So, now we have basically defined your phase angle, our wave numbers that can be represented in the grid. So, now we are in a condition to basically write our input function or any function in terms of our representation of the wave number on the grid, right. So, remember that once you go from the regular grid to let us say in the Fourier mode. So, then it goes basically the phi j will go from minus pi to pi, all the way from minus pi to pi, right. So, let us write our function then. So, if you have a function which is u I and n, okay. So, this is a discretized function I am writing. So, it is similar to, let us say if you are write du by dt equal to nu del t u by del x square, right. So, this u will be written if you use let us say FTCS, right. So, this is u j, if I am doing 1D. So, this will be u I n plus 1 minus u I n by delta t equal to nu, and this is u I plus 1 n minus 2 u I n and plus u I minus 1 n by delta x square, right. This is how you write the FTCS scheme, right. So, we are basically trying to see all this u I n plus 1 or u I plus 1 n and n minus 1 I plus 1 and so on and so forth. We are trying to represent each of these in terms of our Fourier N-search, okay. You use the Fourier N-search to represent this. So, u I n can be written in terms of, so we will take the amplitude of this wave, we will represent that as zeta, okay, and then will be zeta j to the power n, okay, and then it will have certain frequency also, right, or wave number. So, that will be e to the power I, and then it will be, so because we are I am already using I for this representation, this I is basically nothing but the complex number. So, I will what I will do, I will use capital I for the complex number, okay. So, this will become capital I, and then as you write k j into x I, right. So, this is similar to how you represent e to the power I k x minus omega t. So, the temporal part I have basically brought in here, okay. I the n part that you see here is represents time, and that has been captured in your amplitude function, okay. And this will go the j will go from minus n to n, right, like what we had here in the last slide. So, 0 and this goes to n. So, this is all n delta x. So, L equal to n delta x, and this was minus n. Okay. So, this is minus n delta x, right. So, this goes from minus n to n, right. Now, the stability analysis suggests that our amplitude should not grow in time unbounded, right. That is the definition of stability, right. In fact, if you go to the formal way definition of stability, we talk about the error, right. So, we talk about the error. So, if you represent the error, so this is epsilon j n, and we say that the exact solution of the differential equation, okay, discretized equation. So, what is the exact solution, which is the MPD, modified partial differential equation, right. So, let us represent it in terms of okay, if I write sigma I n. So, u I exact n minus u I numerical, right, numerical n, right. So, this is the definition of error, and we say that the difference between these two should not grow unbounded, right, in time. So, so that is why we have taken the time information here, and we will analyze how the amplitude is changing with time, right. So, by the definition of stability we should analyze error, but what we are doing, we are analyzing the wave itself. So, because you know that we say that by definition when we use the one Neumann stability analysis, we consider it to be valid for the linear equation, right. So, if the equation is linear, then what you can write, so n sigma I n will be basically the solution of that equation u I exact n minus u I numerical n, right. And because it is basically okay, so so n is the basically the equation. So, n epsilon I n is equal to n I u I exact minus u I numerical, right. And because this is a system of linear equations, you can write it as n u I exact n minus n u I numerical n, right. And by definition, because we are saying that this is the exact solution. So, n u I exact n will go to 0, and this will be so here it is minus n u I numerical n. Okay. So, basically minus can go away if you consider the difference between the numerical and the exact. Okay, I have considered exact minus numerical, so it does not matter. So, what you can see that I mean the variation of epsilon I n is basically same as the u I numerical n, right. So, either you can analyze the error, or you can analyze the function itself. It does not matter in the von Neumann stability analysis, right, because this u I exact n goes to 0 by definition, and it is a linear, we are analyzing the linear equations, right. And again, do not get confused. So, the difference between this u I exact and u I numerical. So, this is also a solution of the discretized equation. This u I exact n is also solution of discretized equation. This is also the computed solution using your discretized equation, but this can be different because of your round off error, okay, or maybe your prescription of the initial condition, or this kind of thing, right. So, you can either analyze your error, or you can analyze the function itself, it does not matter. So, for convenience we will analyze the function itself, right. So, this is how your function is defined. Now, you can write it as basically u I n, okay, that can be written as, if I take use it a, so it can be written as u I n, and that will be basically zeta 1 n e to the power I k 1 x I. So, x I can also be written as so k 1 x I, just write it like that. Okay. So, x I is nothing but I delta x, okay, and what is k j, equal to j and pi by n, right. This is the k j, right. So, this is x I and then plus zeta 2 n e to the power I k 2 x I, and again I will be basically I and so on and so forth, right. Now, because it is a combination of so many different waves, right, even if you can analyze for one given wave, okay, that will be equivalent to analyzing all these different waves. Why? Because the stability criterion says that none of the waves should grow indefinitely in time, right. So, if you take instead of using this summation function, if you can just take g to the power n e to the power I k x I. So, that is basically we are tackling picking a random wave and we are analyzing that. Okay, so, that is equivalent to analyzing all these different waves, because if this wave grows in time, that means the solution is unstable, right, the scheme is unstable, right. So, this can be written as g to the power n k e to the power I and k j equal to j pi by n. So, that will become I pi by n here and into I delta x, right, and then we will use the definition of phi, okay, which is nothing but pi by n. So, this will become g to the power n e to the power I phi, right. So, this is what we will be analyzing. So, remember this is not the entire function, but just we are picking one wave and we are analyzing it. Okay. So, if you generalize it, then it will become zeta j to the power n e to the power I phi j. Okay. So, I am dropping the j here. So, what did you get from this? Okay. We have basically separated. So, this I represents your spatial discretization and this n represents your temporal discretization, right. So, what we did, we basically separated our spatial discretization from the temporal discretization, okay. And what we want to do, so now basically my u I n is basically g to the power n e to the power I phi, right. So, we have done something I call variable separation. So, that your time is separate from the space, okay. And for stability, what we need to do is this is your amplitude. So, this is our amplitude. So, amplitude should not grow in time indefinitely. So, we have to check whether this zeta to the power n plus 1 to the power zeta to the power n is less than equal to 1 or not. Okay. If it is zeta n plus 1 by zeta by n is greater than 1, basically that means your amplitude is growing in time and then it will basically explode. It will basically become very big and it may explode, right. So, if it greater than 1, then it becomes unstable, right. So, let us take one example of this analysis. Consider one equation, okay. Let us take one equation and which is be del u by del t is equal to nu del 2 u by del x square. Okay. So, this is my diffusion equation, okay. And what we will do, we will consider this f t c s, okay, for one time certain space. So, this represent that will be u I n plus 1 minus u I n by delta t will be equal to nu u I plus 1 n minus 2 u I n plus u I minus 1 n by delta x square. Take nu delta t by del x square is equal to alpha, as we have been doing earlier, okay. So, then you can write u I n plus 1 will be u I n plus alpha u I plus 1 n minus 2 u I n plus u I minus 1 n, right. Now, what does the Fourier inverse say? That my u I n is represented as g to the power n e to the power I and phi, okay. Capital I is square root of minus 1, okay. So, u I n plus 1 will be g to the power n plus 1 e to the power I phi. So, when you increase the time here, it only changes the amplitude. On the other hand, if you go somewhere else in space, it will become g to the power n e to the power I plus 1 phi, right. So, it will only change your exponential part here, okay, the wave representation. Okay, so, put these things here. Similarly, you have u I minus 1 n will become g to the power n e to the power I minus 1 phi. Put all of this in this. Okay, so, this will become g to the power n plus 1 u e to the power I phi, and this will become g to the power n e to the power I phi plus alpha, okay, g to the power n e to the power I plus 1 phi, okay, minus 2 g to the power n e to the power I phi, okay, and plus g to the power n e to the power I minus 1 phi, right. Now, we will go by, you might have read about this Euler number. Okay. What is Euler number? This is e to the power I theta equal to cos theta plus I sin theta, right, and similarly e to the power minus I theta, you can put cos minus theta plus I sin minus theta, which will become cos theta minus I sin theta, right. We will use that definition here. So, this will put g to the power n outside, e to the power I phi outside, okay. This will become 1 plus alpha e to the power I phi minus 2 and plus e to the power minus I phi, right, because you have taken e to the power I phi outside. Okay, so, this will be capital I, okay, which is the wave number. I should use here also capital I, okay, so that there is no confusion. So, you can basically remove this e to the power I phi, and you take this g to the power n plus 1 by g to the power n. So, this is your call your amplification factor, and this is what is our interest. Okay, so, that will become 1 plus alpha, and if you add these two, what will come out? So, that will become 2 cos theta, right. So, here in this will be 1 plus alpha 2 cos phi minus 2, right. I hope I am doing right. So, they will become 1 plus 2 alpha, or just write 1 minus 2 alpha 1 minus cos phi, right, and cos phi can be written as 1 minus 2 sin square phi by 2, right. So, 1 minus cos phi will become 2 sin square phi by 2, that will become 1 minus 4 alpha sin square phi by 2, right. So, in order to basically have this scheme stable, okay, what we need to ensure is that my g to the power n plus 1 by g to the power n is less than 1, right. So, what you need to do is that my minus 1 to, so g to the power n plus 1 by g to the power n mod basically in either side should be less than equal to 1. That means, minus 1 g to the power n plus 1 g to the power n is equal to 1, okay. This will become minus 1 minus 4 alpha sin square phi by 2, okay, and then you can subtract minus 1 from both the sides. This will become minus 4 alpha sin square phi by 2 is then equal to 0, or basically see right now this is sin square phi by 2. So, this is always going to be less than or equal to 1, right. So, this is basically 4 alpha sin square phi by 2 is less than equal to 2, right, or alpha is less than equal to 1 by 2 sin square phi by 2, right. Now, since sin phi by 2 is always less than equal to 1, sin square phi by 2 will always be equal to 1. So, your criteria for the stability of this particular scheme FTCS for the diffusion problem is alpha less than equal to 1 by 2. Now, you can go back and recall when we are trying to solve the our equation using this FTCS, and when you use alpha greater than 0.5, we started seeing wiggle and quickly it became unstable, right. So, that confirms. So, when you use the stability analysis, the same thing is confirmed here, and this is through the mathematical analysis. Okay. So, we will use this stability criteria or stability analysis for different equations. So, right now we have done the explicit, we will do the implicit part of this diffusion equation, okay, and then we will go to the convection equation, we will look at the explicit implicit for both FTCS and FTBS, okay, backward in space and FTCS, so center in space. We know that for the convection scheme, if you use the same FTCS, it should become unstable. That is what we have seen earlier, right. So, whether the same thing comes from the analysis or not, we will see that in the next class. Okay. So, with that we will stop here. Thank you very much.